And of course, today is 10/16/2017. So this hydrogen emission spectra had been observed. This is we already saw this slide together. I just wanted to revisit it because we're going to pick back up with Bohr so that we can jump to the next thing. And we saw these little bands, and you just saw them with hydrogen. You also saw them with some bigger elements. So here's the interesting part. You know, the idea was that there was this difference between a ground state and an excited state, that you add energy to an atom. And what Bohr then suggests is that when you add that energy to an atom, the electrons jump up an energy level. And then when they fall back down, they give off energy in the form of light. You stood on your chairs and jumped down and gave off energy in the form of sound and startled everybody in Mrs. Halett's room, Mrs. Berger's room. What Niels suggested was these tracks, and that because the electrons were locked into these tracks, that's what kept them from getting sucked into the nucleus. And his model worked perfectly for hydrogen. Now, what do we know about the electron in terms of, as we go up the periodic table, as we go from hydrogen to helium to lithium, as we keep adding more protons, what else do we add? More electrons. So the bigger the atom, the more electrons it's got. Did you notice how many lines we had in xenon, which is a much bigger atom? More electrons, right? More electrons coming, jumping up, falling down, more spectral lines. Now, here's the problem. Bohr had done the math, he had done the computation, and he figured out those energy levels, and they worked very well for the first energy level, because hydrogen only has one electron. It's really easy to explain one. When you get up to something like this, this bad boy's uranium, big stuff, his math didn't work anymore. Okay, so it starts to seem like he's on to something, but he doesn't have the whole answer. So now we're going to do sort of another sidebar. I mean, this is 1913. This is pretty early. We're going to do another sidebar because it's not until 1927. This guy, Louis, and he's got like 16 middle names because he's French minor nobility, Louis de Broglie, builds on some work that had been done by Einstein. So if you remember, Einstein's the one who in 1905 proposes that there are actually particles of light. That light behaves as both a wave and a particle. Well, what de Broglie does is he says, what if electrons then behaved as waves? We know that they're a particle. We know that from who? Thomson. Thomson's the one who showed that electrons must be particles. They must have mass because they're actually able to move something inside a cathode ray tube. So de Broglie says, okay, well, if light can behave as a wave and a particle, why can't electrons? He writes, here's the fascinating part, he writes his thesis on this idea and hands it to his thesis advisor. When you do a PhD, you do your research, you hand it off to somebody else who reads it and says, yes, this is reasonable science, or no, this is crazy. And his thesis advisor says, I'm not qualified to judge this, and sends it to the only person on the planet who he figures is, who's Albert Einstein. So Albert Einstein ends up reading de Broglie's doctoral thesis and saying, hey, kid's onto something. So once we have this idea, then we can imagine that all matter, every speck of matter at every point is moving with a wave equation. So I'd like you to take your hand, put your hand up, because I spent a good 30 minutes doing this my sophomore year of high school when I had chemistry, and I learned about this and I thought, whoa! Every cell in your hand is composed of tons of atoms, right? Every one of those atoms has bunches of electrons. As your hand moves, those particles move, and they are also moving as little waves of particular frequency. Ooh. Ooh. The cosmic significance of this should not escape you. I hope you wake up at 3 in the morning thinking, ooh, ooh. That would make me happy. Not to rob you of sleep, but... So de Broglie comes along and says, okay, well, electrons move as waves. Well, if we have something that moves as a wave, we have a wave equation, right? C equals lambda v. Speed equals wavelength times frequency. And if every one of those electrons has a specific frequency, and we go back to Planck's work, where energy is equal to Planck's constant times frequency, and we have C equals lambda v, which is the wave equation, there would be specific frequencies to those electrons that would correspond to the energy levels that Bohr talked about. Oh. Well, if you think about it that way, then suddenly Bohr's idea of these energy levels starts to work for larger atoms. Now, it doesn't work perfectly yet. It's not all the way there, but progress is being made. Progress is being made. Now, and note, de Broglie, he published around 1927. His work was done earlier, and so there had been conversations about this idea. Well, in 1926, largely working with some of the same ideas de Broglie had, Ernst Schrodinger, another good German particle physicist, developed a set of equations. They're called the Schrodinger wave equations that treated electrons as waves. But here's the interesting part. There were only a few specific frequencies that would satisfy the equation. So how many of you have written an equation for anything? You had Algebra 1, right? You can write an equation for a line, yes? It's got a slope, it's got a y-intercept, it's got an x and y component. You can write, as you get into higher maths, you can write equations for lines that look like this. You can write equations for lines that look like this. You can write equations for all kinds of crazy things. Schrodinger's equations treat the position of electrons as things that exist at specific points in space. Sort of impose that Cartesian coordinate system onto this imaginary atom, and then write an equation for where that electron is found. And when you do that, there are only specific locations in which they can be found. There are only specific frequencies that work. You can have an equation that doesn't work. If you go on to take calculus, you'll learn about vertical and horizontal asymptotes, which is just fun to say. Asymptote. Asymptote. You can call your best friend an asymptote. You're just talking about a line that approaches a point but never gets there, because there are certain values that won't satisfy the equation. Same thing happened with Schrodinger stuff. Now, at about the same time, Werner Heisenberg, my favorite dead particle physicist, I have this crazy dead physicist crush on Werner Heisenberg. I'm convinced that had we lived at the same time in the same neighborhood, we would have been best friends, and we would have had coffee together every day at 4 o'clock and cake. But that was not to be. So anyway, Heisenberg is working out, and you'll see references to matrix mathematics. At the same time, Heisenberg is working with some other ideas. And in 1927, he publishes what becomes known as Heisenberg's uncertainty principle. And what it says is that you cannot know both the position and the velocity of an electron. That the act of observing one of those changes the other. Now, this goes back to Einstein's work with the photon. What does it take for me to see this bottle? What is required? You all see this bottle? Okay. What's required for you to see this object? Light. Light. Light's got to bounce off the object. So a stream of light rays or light photons have to hit this thing. They have to bounce back to my eye. And then my eye forms an image which my brain interprets. To see anything, that's required. Light has to hit an object and bounce back. Think about how tiny, what's the mass of an electron? I'm not asking you to spout it off, but it's little. In order to observe an electron, it has to be struck by a photon. The act of a photon striking an electron is enough to change its position and or velocity. So by observing one, you negate the observation of the other. You can't observe them both. So you can know with some degree of certainty either its position or its velocity. You can never know both at the same time. And it gets, the math gets pretty complicated, way, way, way above my pay grade, like light years above my pay grade. I'm a biologist. These two ideas together, though, and the interesting thing, the thing that I find funny, Schrodinger and Heisenberg, all through the 1920s, were sort of at odds with one another. They were like opposing camps in terms of particle research, where Schrodinger thought Heisenberg was wrong and Heisenberg thought Schrodinger was wrong. Turns out they were both approaching the same idea from opposite directions. They didn't know it till they met at the station, so to speak. Because both of their ideas build into what becomes known as the quantum model of the atom. So we had, if you recall, okay, whose is the first model? Dalton's model of the atom. Then we have whose model of the atom? Thomson's, the plum pudding model. Then whose? The first planetary model, which is Rutherford's planetary. Then whose? Fixed orbits, not orbitals, but orbits, fixed energy levels outside the positive nucleus. This is, well, I don't want to bore you. Bohr. What's sometimes called the Bohr-Rutherford planetary. And now what we're coming up on is what becomes called the quantum model. So the quantum model looks pretty weird. We have a small, dense nucleus, and out in space all around it is this area. This area in which anywhere there could be electrons. This is the quantum model. And if we were going to attach names to it, it could almost be called like the Heisenberg-Schrodinger quantum model, though we don't do that. We just call it the quantum model, really because the work of so many people went into developing the quantum model. I mean, without Einstein's work, without de Broglie's work, without Planck's work, we wouldn't have gotten to the quantum model. Heisenberg and Schrodinger kind of push it over the cliff. They're the icing on the cake that gives us the quantum model. So let's define the quantum model. Okay, so in the quantum model, dense central nucleus, protons and neutrons, which we've known for a while. Okay, Rutherford's model had that. Rutherford didn't know about neutrons, though he had proposed that they must exist. Chadwick finds them in the 30s. Yeah, so actually at the time that the quantum model starts to be proposed, we still aren't sure of the identity of those massive neutral particles. There are electrons that are in specific areas outside the nucleus and that are in constant motion. In such constant motion that we can't actually pin down where we are. The big holdover from the planetary model is the idea that there are main energy levels. But they're no longer those little sort of orbits, like planets around a sun that we had imagined. They're now something a little bit different. See that marble inside a cloud of cotton candy? That's the quantum model. So in the quantum model, we can't know the position of an electron, ever. We can't pin it down. And that's Heisenberg. But when we solve Schrodinger's wave equations, what we get are three-dimensional areas of space where there is a high probability of finding an electron at any given time. And those areas of high probability are called orbitals. Note that orbital is not an orbit. They are different things. An orbit is a nice little racetrack that the atoms go around. An orbital is a big, fuzzy, cotton candy kind of cloud. Somewhere in there, there's probably an electron. But we can't pin down where. We don't know where at any given point. So, here's the question people ask next. Which one's right? But that's not how science works. It's not that one is right and one is wrong. One gives a more complex and complete picture of the atom, but we use them both. And if you had physical science and you learned main energy levels and you learned to count 2 electrons on the first and 8 on the second and 18 on the third, what you were actually doing was really using the Rutherford-Bohr planetary model. It's a really convenient tool. It's a simplification, but sometimes it's good to simplify. If you've seen a little model of the solar system and the sun and all the planets lined up around it, they usually simplify those. They simplify the orbits, they simplify the position of the planets. Very often they leave out the asteroid belt, because how do you show an asteroid belt on a mobile? That's okay. It's okay to simplify sometimes. Using both models is actually helpful. So that gets us pretty much to what we know today. I'm going to publish the full set of notes to Classroom. You can use them as a resource if you want. And I'm going to give you the rest of the time today to work on modifications, edits, updates, etc. to your projects. Those will be due Friday, but I don't anticipate any more time in class to work on it, okay? So that's it. That's where we stop.